So now we're going to cover what to do if your shear stress is not constant over your whole surface area. All right, and this is going to be a review really of math methods that you've already had. So first let's review what we've learned in fluids. The no slip condition, the velocity at the surface is the same as that of the surface. Hopefully you're starting to remember that. Boundary layer is the area near a surface where the velocity is not changing, or du dy is 0. And shear stress again is mu du dy, or if we have a cylindrical coordinate system with just velocity going in one direction, just changing in the r direction, we can also say mu du dr, which you would see down here as well. Cylindrical coordinates say pipe flow, flow flowing in a pipe, where the velocity is only going in this direction and it's only changing with r. And then the last thing we learned was a small gap approximation, which is a simplification of your mu du dr or mu du dy. And in that case, we can plug in a delta u over h for our du dr and simplifies things. Okay, so if you want to find shear force over a whole surface, but the shear is changing over that surface, if you remember from math methods, what you need to do is integrate over that whole surface. Okay, so to find that total F, the total force, basically you have to do a double integral over that whole area. And our shear stress exists at a point. Okay, but if you cover all those points or all those dAs with your integral, then you can come up with the total force. You could use a similar thing for the total moments. So one of the trickier parts of these problems is figuring out what your dA is. So I've got a few hints here. One of the things you can do is, if nothing is changing in one of your directions, instead of doing a dx dy like I have up here, instead make it into a sliver. Okay, so let's say here is your surface, and this is your x direction. Say this is your z direction. If the u isn't changing or nothing is changing across the x direction, just make this in a sliver. So there is now your dA, and if this is width w, then your dA is going to equal w dz. All right, and the advantage of this is now you just have a 1 dz, so you just have to integrate from whatever this z value is to whatever this z value is. Okay, so it's a single integral instead of a double integral. One of the things in polar coordinates that you come across all the time is some sort of arc. So if your little dA is some sort of pi-ish looking piece, where we're talking about a d theta here, the distance from here to here is going to be r d theta. This distance is dr. So your dA is actually going to be r d theta dr. Okay, let me rewrite this little. r d theta is that distance across. All right, so we can then apply sort of both of these things together. So if you have polar coordinates and nothing is, say, changing in the theta direction, then let's say you're looking up at a disk and you want to integrate over that whole disk surface, but nothing is changing as you go around. It's all the same in that direction. Then you can draw yourself a little dA that's circular. It has a width. Maybe if this is a flat disk, that width would be dr. All right. This dA then would be 2 pi. So this whole distance around here is 2 pi r. It's the circumference. 2 pi r, and then times the width, dr. Whatever that width is. We'll have a problem down here where it's not dr, but you can use whatever width that is. All right, so those are really the 3 tricks in finding your dA. if you want to find the total force on a surface and the shear stress is changing over that surface, you got to start with the force at a point, and the force at a point is dF. And that dF, tau exists at a point, so you don't have to make a d tau. That's going to be tau dA. All right, so dF is tau dA. You could also have a moment. If you have something spinning, say this disk is spinning, a moment due to that point force is going to be a d moment, right, at that one little spot. And that then is going to be r dF, okay, where r is the distance from your axis of rotation. Okay, so let's use this stuff in a little example. We're just going to set this example up. We're not going to actually do the whole thing. So what this is a cone and plate viscometer, it's called. So this cone is spinning on top of some fluid. Okay, this might be oil, that pink part. And the purpose of this cone and plate viscometer is to figure out what the viscosity is. So you apply a torque, and you measure that torque, and you also measure the speed, the rotational speed, omega, that thing spins. And if it's a real thick fluid, it's for the same torque, it's going to spin slower than a thin fluid. So that's going to give us an idea of what the viscosity is. So let's assume that it's Newtonian, incompressible fluid, and let's do a small gap. So the way these are made are so that this is a short distance between here. So we can have a small gap approximation. Okay, so you see this is a spinny round thing. You see R's in here. So I would think we're going to use a polar or cylindrical coordinate system. Okay, so let's draw that coordinate system. So if this is our Z, that's our axis of rotation. R is going to be some distance, and we'll say it's out to the surface of that cone at any spot. So what we're going to be doing here is we're not going to be summing forces, we're going to be summing moments, right? So the sum of the moments, because it's spinning around, call this A, our axis A, that has to be 0 if it's not speeding up. So if it's at steady state, spinning at a constant speed, that's got to be 0. So M, we're going to call the torque that's applied M. Okay, that's going to have to be offset just from the moment due to the shear stress on that surface. So that has to equal M, we'll call it M shear, okay? And, but if you look at this, the velocity is going to be changing on this surface. So this M shear is due to the shear stress all over this surface, okay? But as you go out, the velocity is going to be increasing. So the velocity is changing, and not only that, also in our equation is this h distance, and that is also going to be changing as we go from 0 to big R. So we know we're going to have to integrate. Okay, so this total moment due to shear is going to actually equal the integral over that surface, right, of dm shear. Okay. Luckily, we have a formula right up here to help us out with that. So M, which is that applied torque, which is a given, we want to have M in our answer, so let's leave the M there, that's our applied torque. That is going to be equal to the integral of dm from the shear. Okay, well dm from the shear is RDF, right? So it's this perpendicular distance from the axis of rotation that particular dA sits, that gives us that dF. Well, the dF from up here is going to be the integral then of R, and then our dF is tau at that surface times dA. All right. So if we look up at this cone, we get something that looks kind of like this circle up here. And if you think about how this is spinning, there's not going to be anything different if we're at this spot on the cone or that spot, as long as we're at the same R value, which means we can make a sliver. So let's make a sliver. Okay. So we are on that cone surface and we have a sliver, and here's our little dA. Okay, but the problem is, if you look at dr is in this direction. But on the cone, it's not quite that distance. What we have, we'll call it something else. Let's call it dl. Okay, so our dA is going to still be that circumference, 2 pi r. Okay, but then the width is dl. Okay, so we have a problem. When we plug this dA in here for our equation, we have L's and R's, and we don't want L's and R's. We just want R's, and we want to integrate from R equals 0 out to R equals big R. Okay, so what we're going to have to do then is use some trig for dl. Okay, to plug in, so we end up with a dr instead of a dl. Okay, and we'll do that in class. All right, a few last minute notes on viscosity. Remember, viscosity varies with temperature a lot, but the weird thing is with liquids, as you heat up liquids, the viscosity decreases, but the opposite happens with gases. Okay, kind of weird, but that's the way it is. Mu, we've been calling this viscosity. It's really dynamic viscosity. Okay, and we differentiate that from what we call the kinematic viscosity. In kinematic viscosity, Greek nu, okay, it looks kind of like a V. That's defined as mu over rho, and really it's just a shortcut so that we don't have to look up both mu and rho and then divide. Instead, we just look up nu sometimes. Notice also that viscosity varies a lot among different fluids, all the way from 10 to the minus 5 up to 1.5. So glycerin very, very thick, air very, very thin. So that concludes our viscosity and shear stress talks, and now you should be able to solve all your viscosity problems. There are a few more things in chapter 1 that we'll just touch on before I let you go. One of those is a Reynolds number, and Reynolds number does involve viscosity for sure. So Reynolds number tells you whether it's laminar or turbulent, or how turbulent something is. So when it's laminar, it is dominated by viscosity. And if it's turbulent, it's dominated by inertia. Okay, so the Reynolds number gives you an idea, which is it, laminar, turbulent, or how turbulent. So it's going to be some characteristic velocity times some characteristic length over nu. Nu is our kinematic viscosity, or rho times characteristic velocity times characteristic length over mu. Okay, same thing. So for instance, if you have flow over, say, a telephone wire, the characteristic length of that telephone wire is going to be the diameter. And the incoming velocity of that wind speed is going to be your characteristic velocity. So what are those characteristic lengths and velocities depends on what your problem is, and you want to pick the most important velocities and lengths for that. So the Reynolds number for this, Reynolds number, and we'll usually use a subscript to indicate what our characteristic length is. Reynolds number based on d is going to be u infinity d over nu. Okay. Something that you'll see in heat transfer, thermal conductivity, it has a K. It's kind of analogous to 1 over mu. So high thermal conductivity, heat flows really well. Okay, kind of corresponds to a low mu for flowing. Surface tension, some fluids like various other solids, say, so if this is a glass capillary tube, water will rise up the capillary tube because water actually likes glass better than it likes itself. So that's wetting the surface. And let's say we put mercury in that same glass tube. It does not care for glass. So it is non-wetting. And that's how it will look. It won't rise, it'll actually shrink down inside that tube. All right, vapor pressure. Vapor pressure we had in thermo has to do with cavitation, right? So if you have a low enough pressure, so if you have a high velocity, you get a low pressure. If you have a low pressure, you can cavitate. So high velocities can cause cavitation. That can be a real problem in pumps and turbines. Something to keep in mind. And finally, last thing for this chapter is the speed of sound. And we're not going to really use do supersonic kind of problems, but what we're going to do is just incompressible problems. Okay, and incompressible is going to be if the Mach number is less than about 0.3, what we can do is assume that rho is about constant and our flow is approximately incompressible, even if it's something like air, as long as the temperature is not changing too much too. So for an ideal gas, we actually have an equation for the speed of sound. Speed of sound is A, and it's going to be the square root of K R T. R is the gas constant, T is the temperature, K is the specific heat ratio. Okay. For air, we get 340 meters per second. For helium, we get something much higher, which is why your voice sounds a little bit high if you're on helium. Ha! Higher frequency. So there's an interesting topic. So the way we're going to use Mach number in this class is just to decide, is it incompressible or is it compressible? So as long as we're below about a Mach 0.3, it's incompressible. And the Mach number is just the velocity of whatever you're talking about divided by the velocity of the speed of sound. So if it's less than 1, Mach number less than 1 is called subsonic. Greater than 1, supersonic. And greater than 10 is hypersonic. And just in case you do crossword puzzles, SST stands for supersonic transport. So your Concords, military jets. All right, so go ahead and finish the quiz, and that'll do it for chapter 1.